Hi, this is Mrs. Sykes, and this is probably the most complicated enzyme video that I'm going to do. This one, instead of looking at individual enzyme graphs or identifying which of the curves matches which of the organs, this one is about using pH as a measure of how a reaction is occurring. So instead of drawing a lovely little test tube and counting how many bubbles there are versus one with more bubbles in and going, oh look, this one has a higher rate of reaction. This is far more scientific. This one is using pH as our measure, using pH as our dependent variable, and that can get quite tricky. So we need to have a quick review of the pH scale. So I have included some of these numbers on here for my pH scale because only some of these numbers are really relevant for biology. But to help you out, we've got acid down this end. Acid is our red end, our yellows, our oranges. Down this end, which we're not really going to use because it's not very relevant for the body, we have the alkali end, which is where we get to blues and purples on our universal indicator scale. And then here at 7, we would have neutral, which means that it's neither acid or alkali, perfectly balanced between the two. Now in our body, we have got 3 organs that you need to know about in our digestive system. We've got our stomach, which is at pH 2. We've got our mouth at pH 7, and we have our small intestine at pH 8. And depending on where an enzyme is found will depend on if it has an optimum around 2, an optimum around 7, or an optimum, its best level, at around pH 8. Okay, so in our body and in our digestive system, we have proteins that need to be broken down, and we have fats that need to be broken down. When a protein is broken down by the enzyme protease, it releases amino acids. Fats, when they break down, release fatty acids. Fatty acids and amino acids are obviously acidic. The glycerol doesn't make any difference. When we break down starch into sugars, it doesn't make any difference. It's neither acid nor alkali. But protein digestion and fat, or lipid it's sometimes called, fat or protein digestion release acids. So if we had a test tube that started at pH 7, and in our test tube we had some fats, and we added the correct enzyme into that test tube, what would happen is they would begin to break those fats down and release fatty acids and glycerol. Oh, fabulous. But now that it's got fatty acids in it, instead of just fats, it's going to push the pH slightly closer to acidic. If we break down even more of our fat into fatty acids and glycerol, it's going to push the pH even further down toward the acid end. So every time a fat molecule is digested and turned into fatty acids and glycerol, the pH is going to get lower and lower and lower because there is suddenly more acid available in that test tube that you are measuring. Another way of looking at this is if we have pH up the side, which is quite unusual, and if we have time. And again, we still have our test tube with our fats in, and we are going to add an enzyme. In this graph, you can see that we have a constant level of pH, and then it goes down, and then goes constant again. This is the reaction profile, the story, if you like, for what happens in that test tube. So you have a test tube, and in that test tube, you have some fats. And then at some point or other, you add in the enzyme. In this case, it's going to be lipase. And that lipase enzyme will take those fats, and one by one, it will catalyze them, break them down into fatty acids and glycerol. And when it breaks them down into fatty acids and glycerol, the pH will become more acidic because of the acid bit, so the pH will fall. So this bit here, this is the reaction taking place because the pH is going down. So this is where the reaction is taking place. This level here is where the reaction has finished. Most likely because every single fat molecule has already been used up. Here, it's waiting to start. So there is no reaction at this point. I would suggest that that means that this is the point here where we put the enzyme in. So we've added lipase at this stage, and as soon as it's there, it starts to break down fats into fatty acids and glycerol, and because of the acid, the pH goes lower. Because if we remember, lower is acidic. And as that goes more and more and more and more and more acidic, we've broken down more fat. But eventually, all of the fat molecules are no longer there, and they are now all fatty acids and glycerol. And that's all that there is left. And if there's no more fats to break down into fatty acids, then the pH is not going to go any lower. So, let's review. In our body, we have got 3 major organs that you need to know about the pH. Stomach, pH 2, mouth, pH 7, small intestine at pH 8. If we are using an experiment that breaks down protein or fat, quite often they use milk, they might use universal indicator as a way of finding out how well the reaction is taking place. It'll start off around 7, and then as more and more of the fat or the protein, or both, is broken down, the pH will fall as acids are released. When it stops falling and stays steady, you know that the reaction has finished. If you have a situation where you have 2 test tubes running directly opposite each other, so running at the same time, one gets to here in a minute and the other one gets only that far, you would know that the one that didn't get quite so far wasn't working as well. So this one was more efficient. It had got further, a bigger change, more digestion in the same amount of time. So, proteins and fats can be broken down, and when they are broken down, they release acids. And we can use that acid digestion, so the acid being produced, to track how the enzyme reactions are taking place.